Good morning, guys. We are in fourth unit. Almost today we will complete this fourth unit. This is the 10th lecture in unit 4. So the last topic is engineering properties of rocks. Guys, so in this engineering properties of rocks, the main contents are introduction and physical properties of rocks, methods of determining rock properties, geological characteristics of rocks, general characteristics of rocks, modulus properties of flexible strength or elastic properties of rocks, engineering uses of rocks, and conclusion. These eight subtopics are we discussed in engineering properties of rocks. Guys, the main objective of engineering properties of rocks is to aim of this lesson is to understand the important physical properties of rocks and their determination, geological characteristics, general characteristics, modulus properties of rocks, building stones, and their occurrences. The role of a geotechnical engineer is also highlighted. Guys, the introduction means engineering properties of rocks is a collective nomenclature which includes all such properties of rocks that are relevant to engineering application. After their extraction from natural beds or without extraction, that is in situ conditions. The first set include all those properties for which a rock must be tested for selection as a material for construction, such as a building stone, road stone, or aggregate for concrete making. The second set of the properties include the qualities of natural bedrock as and where it exists that would determine its suitability or otherwise as a construction site for a proposed engineering project. Obviously, in both cases, the economy and safety of an engineering project are generally dependent upon the proper understanding and determination of the engineering properties of rocks. Engineering properties of rock are controlled by the discontinuities within the rock mass and the inherent properties of the intact rock. Therefore, engineering properties must account for the properties of the intact rock and for the properties of the rock mass as a whole. A combination of laboratory testing of small samples, empirical analysis, and field observations should be employed to determine the requisite engineering properties. Rock properties can be divided into two categories: intact rock properties and rock mass properties. Intact rock properties Intact rock properties are determined from laboratory tests on small samples, typically obtained from coring, outcrops, or exposures along existing cuts. Common engineering properties typically obtained from laboratory tests include specific gravity, point load strength, compressive strength, tensile strength, shear strength, modules, and durability. Here, guys, rock mass properties are determined by visual examination and description of discontinuities within the rock mass. It should follow the suggested methodology of the International Society of Rock Mechanics and how these discontinuities will affect the behavior of rock masses when subjected to the proposed construction. Guys, here are the physical properties of rocks. In most of the engineering applications, rocks are used as building stones. A building stone may be defined as a rock that can be safely used as a rough unit or as a properly cut and shaped or a dressed block or slab or column or sheet in a different situation in an engineering construction. The following physical properties are considered to be important for a rock to be used as a building material. Crushing strength. It is also termed as a compressive strength of a stone. It may be defined as maximum force expressed for a unit area which a stone can withstand. Any force behind the compression strength will cause a failure of the stone. Mathematically, compressive strength is expressed by a simpler method as follows. So guys, uh, C naught is equal P by A. Here where C is equal compressive strength, P is equal to load at failure. A is equal to area of cross section of stone under P. The determination of compressive strength of a building stone involves making standard test specimens which are either cubes of 5 centimeter side or cylinders of length, diameter ratio of 2 or 2.5. These specimens are then loaded gradually one at a time after placing on the base plate of a universal testing machine. Till the first crack appears in the specimen, any further loading will crush the specimen. The compressive strength determined in this way using the above relationship is called unconfined or universal compressive strength because the test specimen has no lateral support or resistance. When the compressive strength is tested by a method providing lateral support as by keeping the specimen in a special cell filled with a liquid under pressure. The value obtained then it is called a confined or triaxial compressive strength. The crushing strength of a rock depends on a number of factors such as its mode of formation, composition, texture and structure, moisture content, and extent of weathering it has already suffered. Igneous rocks are crystalline rocks. They are compact and characterized by interlocking in texture and uniform in structure. These rocks possess very high crushing strengths compared to sedimentary and metamorphic rocks. In the sedimentary and metamorphic rocks, the presence of planes of weakness along bedding planes, foliation and schistosity and cleavage greatly affects the compressive strength both in direction and magnitude. The sandstone may show a very low crushing strength when loaded parallel to bedding planes than when loaded perpendicular to the same structure. Except for sandstone, quartzite, and most other sedimentary and metamorphic rocks are composed of clays, calcareous and hydrated silicate minerals which are inherently weak in strength. Crushing strengths of common types of building stones are generally higher than the loads that they are supposed to withstand in ordinary type of building constructions. The guys, here the compressive strengths of some rocks and their range are as follows. They are expressed in kg per centimeter square. A dolerite 1500 to 3500, and a basalt 1500 to 3500 kg per centimeter square. Quartzite 1500 to 1500 to 300 kg per centimeter square. Granite 1000 to 2500 kg per centimeter square. Marbles 700 to 2000 kg per centimeter square. Gneiss 500 to 2500 centimeters kg per centimeter square. Sandstone 200 to 2500 kg per centimeter square. Limestone 200 to 2000 kg per centimeter square. During the last few years, thousands of tests have been made to classify the rocks on the basis of uniaxial compressive strength into grades. The following classification proposed by Deere and Miller has been found useful. Class A is here class description uniaxial compressive strength kg per centimeter square. Very high strength more than 2240. B is the high strength 1122 to 22 to 40, and C medium strength 500 to 1120, and D low strength 200 to 500 kg per centimeter square. Very low strength less than 200 kg per centimeter square. Here guys, next transverse strength. It is defined as the capacity of the stones to withstand bending loads. Such loads are only rarely involved in situations where stones are commonly used. But when a stone is intended for use as a beam or a lintel, its transverse strength is determined as modulus of rupture using the following relationship. R is equal to 3WL by 2BD square. R is equal to modulus of rupture. W is equal to weight at which sample breaks, and L is equal to length of the specimen. B is equal to width of specimen. D is equal to thickness of the specimen. This property is determined practically by loading transversely a bar-shaped test specimen. Generally of this property is determined practically by loading transversely by a transversely a bar-shaped test specimen. Generally of this property is determined 20 cms into 8 cm into 8 cm dimension, and is supported at the ends from below. It has been found that in stone, the transverse strength is generally 1/20th to 1/10th of the compressive strength. Shear strength. Shear strength is the resistance offered by a stone to shear stress, which tends to move one part of a specimen with respect to the other. It is obtained by using the relationship. Shear strength of a stone is also not commonly determined except when the stone is to be used as a column. S is equal to P by 2A, where P is equal to load at a failure, A is equal to area of cross section of the specimen. It has been observed that shear strength of most common building stones ranges from 70 to 140 kg per centimeter square. In laboratory testing, a bar-shaped specimen is held with grit and is supported at the ends below, is loaded from above. Rupture occurs when the shear strength is exceeded. Tensile strength. Tensile strength of a rock is related to its ability to withstand breakage. It happens after some level. That level is its strength. It may be determined directly or indirectly. The tensile pulling strength that has to be applied to a material to break it. It is measured as a force per unit area. The direct method would require elaborate means to avoid bending while applying tensile forces by gripping the specimens at the ends. Since tensile stresses are seldom required accurately, an indirect method is commonly applied. The indirect method is called the Brazilian test. It consists of loading a test cylinder diametrically in such a way that the applied loads would develop tensile rupturing along the diametrical plane of the specimen. Loads are gradually increased till the cylinder fractures. The load P at rupture being thus known, transverse strength T is calculated by using the formula Ts is equal to 2P by mu dl. D is equal to diameter of the specimen, L is equal to length of the specimen. Here guys, porosity, the shape, size and the nature of packing of the grains of a rock give rise to the property of a porosity or development of pore spaces within a rock. Numerically, it is expressed as the ratio between the total volume of free spaces and the total volume of the rock sample. Porosity is commonly given in percentage terms, presence of interlocking crystals, angular grains of various sizes and abundant cementing materials are responsible for low porosity of stones. Conversely, the rock will be highly porous. It composed of spherical or rounded grain sandstone, or if the cementing material is distributed unevenly or is of poor character. Porosity is an important engineering property of rocks. It accounts for the fluid absorption value of the stones in most causes, and also that a higher porosity significances a lesser density, which generally means a lesser compressive strength. Porosity values for a few common building stones: granite 0.1 to 0.5, basalt 0.1 to 1%, sandstone 5 to 25%, limestone 5 to 20%, marble 0.5 to 2%, and quartzite 0.1 to 0.5%. And absorption value is, it defines the capacity of a stone to absorb moisture when uh, immersed in water for 72 hours or till it gets the full saturation. It is generally expressed in percentage terms of original dry weight of the mass. It may be obtained from the relationship absorption value Ws minus W naught by W naught into 100, where Ws is equal to weight at saturation, W naught is equal to dry weight of the sample used. Permeability. It is the capacity of a rock to transmit water. Sandstones and limestones may show high values for absorption or 10% or even more. Selection of such highly porous varieties of these stones for use in building construction, especially in most situations, would be greatly objectionable. Presence of water within the pores not only decreases the strength of the rock, but also makes the stones very vulnerable to frost action in cold and humid climate conditions. Guys, here the density, it is defined as weight per unit volume of a substance, but in the case of rock, it is not only the solid mineral matter which wholly accounts for the total volume of a given specimen. A part of the rock may comprise of pores or open spaces which may be empty. partly filled or wholly filled with water. Accordingly, three types of density may be distinguished in rocks. They are dry density, bulk density, and saturated density. Here, guys, what is the dry density? It is the weight per unit volume of an absolutely dried rock specimen. It includes the volume of the pore spaces present in the rock. The bulk density, it is the weight per unit volume of a rock sample with a natural moisture content where pores are only partially filled with water. Saturated density, it is the density of the saturated rocks or weight per unit volume of a rock in which all the pores are completely filled with water. The fourth type is also recognized as a true density. It is the weight per unit volume of a mineral matter without pores and water, of which a rocks made up. The most engineering calculations, it is the bulk density which is used frequently. Bulk density values in gram or cubic centimeter for some common building stones are granite 2.7, basalt 2.9, sandstone 2.6, and limestone 2.2 to 2.6, and abrasive resistance. It is more a qualitative than a quantitative property. It may be broadly defined as the resistance which a stone offers to rubbing action of one kind or another. Determination of this is of considerable significance when stones are intended for use in situations where rubbing by natural or artificial causes is involved. As a routine example, stones used in paving along roads, facing stones in buildings of arid region where strong sand laden winds are blown. Those type of situations demand stones that have not only high abrasive resistance but also of essentially uniform composition so that the wall is as uniform as possible. Stones composed of more than one mineral like granite may look quite appealing in such cases when freshly used, but within short time they may get pitted or are disfigured because of unequal wear of the different mineral components. Frost and fire resistance. Many building stones show quick disintegration of building stones or rocks when used in situations involving frost formation, excessive cold, or heating. Frost causes disintegration by expansion of water and breezing within the rock pores. In the case of fire, the unequal expansion in different mineral components and also at different depths from surface inwards may cause disintegration. This effect becomes more pronounced when the rock is first heated and then suddenly cooled by water. Heavy stones, including granites, crumble to uh, peace under such a treatment. It is easy to understand that rocks which are found porous and weak in strength are easily deteriorated in cold, humid climates by frost action. Limestone and sandstone fall in this category. They show very poor frost resistance. Fire resistance is especially determined when the stone is intended for use around stoves, heating places, and in the wall of furnaces. Only compact and massive sandstones and quartzite shoot reasonably well in fire and heating places. Next, method of determining and rock properties. Subsurface rock properties are generally determined using one or more of the following methods: in situ testing during the field exploration program, laboratory testing, and back analysis based on site performance data. In situ field testing. The geotechnical engineers are expected to determine various soil and rock parameters under natural in-place conditions. This type of testing is useful for projects where obtaining representative samples suitable for laboratory testing is difficult, such as those involving soft clays, loose sands, or soils below the water table. Common in situ tests are performed in conventional drill borings, whereas specialized tests require a separate borehole or different insertion equipment. Field in situ borehole tests can be grouped into three categories: correlation test, standard penetration test (SPT), dynamic penetration test (DPT), and strength and deformation test. Penetrometers such as cone penetrometer test CPT and piozone, piezo cone and penetrometer test PQS and pressure meters PMT such as Menard and self boring and dilatometer. Stress or shear devices such as van shear and borehole shear test. Permeability test, pump test and sludge test, water pressure test, hydraulic conductivity test, percolation test. Here, laboratory testing of rocks. Rock strength is measured by laboratory testing. Strengths are very different depending on the stress field applied to the rock. All rocks and soils are very much stronger in possessing comparison strength than in tensile strength. The two common laboratory tests to determine the compressive strength of the rocks. Uniaxial and confined compression test. In this method, a cylindrical rock core is loaded axially until it fails. Triaxial confined compression test. In this method, a cylindrical rock core is placed in a cell subjected to all around confining pressure by a hydraulic coil acting through a thin impermeable membrane and loaded axially to failure. There are a variety of tests used to determine the tensile strength of rock. Direct full test. Um, in direct full test, a cylindrical rock core sample is anchored at both ends and stretched. And Brazilian test, a relatively thin disc is loaded across the diameter until it splits. Beam flexure test. A thin slab of rock is loaded vertically when supported at 3 or 4 points along its length. Back analysis based on site performance data. Back analysis is a quantitative approach to adjust soil or rock properties to match measurable site performance. Back analysis is a method used to determine engaging properties of soil or rock. It is often used with geotechnical failures. When failures occur, excuse me guys. అమ్మాయి చేశాడు sorry guys. And so Back analysis based on site performance data. Back analysis is a quantitative approach to adjust soil or rock properties to match measurable site performance. Back analysis is a method used to determine engineering properties of soil or rock. It is often used with geotechnical failures. When failures occur, back analysis can be used to model the conditions and loads which resulted in failure. Back analysis can also be used in some situations where failure has not occurred, but the geotechnical performance can be quantified, that is, deformations. Back analysis is a quantitative approach to adjust soil or rock properties to match measurable site performance. Most back analysis in geotechnical engineering are based on the methods that utilize field displacement monitoring data. Following are the methods of back analysis. Back analysis of slope, back analysis of soil settlement resulting from the changes in loading, back analysis of foundations, use of numerical modeling for back analysis. Here, geological characteristics of rocks. Uh, Okay, guys, in our next class, I will tell you geological characteristics of rocks, mineralogical composition. Thank you, guys, for all of your support. In next class, I will tell you the next topic.